We want to welcome all of you who are here tonight. I should ask one other question. How many of you are here for the first time tonight? A fair number, that's good. So for those of you who are here for the first time, and for others who may not remember, our goal here is to have thoughtful discussion. We hope that people show up here because you're curious, because you're interested, because you have ideas, but not because you have a closed mind. And I know that every program we've had, I've learned things that I hadn't understood or thought about before. That might mean that for those of us who have a more extreme view on one side or another of an issue, that we might find ourselves moving closer to the center, not because everything is muddy, but because there are more nuances to many of these questions than the simple answer, the simple black and white answer. So tonight's topic comes directly from the recent accident in the Gulf with the BP oil spill, and leading us to think what would be an important issue for us to look at. And we weren't going to ask, is it ethical to have oil spills, but we were going to ask, what are the ethics of dealing with energy considerations? And one of the big questions that came to mind was, what should we be doing in the long term about the fact that petroleum, that fossil fuels, these products that we use in every dimension of our lives aren't going to be here forever. And in fact, as time goes on, whatever is left is going to be harder and harder to get and more expensive in various ways. So one of the best approaches we could think of to dealing with this was to ask about what are the alternatives to the energy sources we now use primarily. And we are extremely fortunate to have found somebody who is here in San Diego and is now at UCSD, who can speak to these issues from a great deal of authority. And if you had his bio sketch, which you normally would, then I would just refer you to that. But since you don't, I will note a couple of things. Our speaker today is Steve Mayfield. His PhD is in molecular biology from UC Berkeley. He's been in San Diego for a fair number of years, but particularly of note for tonight's program, in 2007, he was became the founding director of the San Diego Center for Algae Biotechnology. He is now a professor at UC San Diego. Scientifically, his background is that while he was an assistant professor at Scripps Research Institute here in San Diego, Steve was the first person to successfully transform the nuclear genome of C. reinhardti, an organism that can be used for the study of photosynthesis and gene function. And that work has been key to a lot of work that's being done now relevant to trying to modify algal organisms in order to produce energy. Separate from that, Steve wanted to make sure I let you know for full disclosure purposes that he's also formed a company that has a goal of developing biofuel production through metabolic engineering of algae and photosynthetic bacteria called Sapphire Energy. So from that wide range of background, he is an ideal person to tell us about alternative energy sources and help us through the discussion for tonight. So I want to welcome Steve, and I will switch his slides over to his slides here.
Okay. Full screen. Go to window. Yeah, and I think it should say, does it say full screen? Yeah, there you go. Okay. Can I wander around kind of like Phil Donahue, who was the old talk show host? Well, thank you all for coming out tonight. I know that this is supposed to be a discussion. I don't want this to be too much of a lecture, but I did want to put some facts across because probably like many of you, I was happily going about my life being a professor and working on trying to understand gene expression when about a half a dozen years ago, it started to become obvious to me, and really obvious over the last 3 or 4 years, that we better start to do something about our energy issue. Obviously, as I'm sure many of you have heard on the news, every president since Dwight Eisenhower has said that, our energy policy has to be reformed, and yet we continue not to do that. And maybe now I hope that enough things have collided, the perfect storm maybe has shown up, and we'll start to do something about that. But over the last 3 years, I really sort of started to educate myself on, what is the energy landscape in this country, and what should we be thinking about sort of going forward. And so I want to give you some of those sort of facts first, and then hopefully that'll roll into a discussion. Okay? And by the way, that picture at the bottom is the algae that grows up in the salt ponds that are just on the south end of San Francisco. So you see those if you ever fly into San Jose Airport. Look out the left window and you'll see them. That's a little green algae called Donnelliella salina. So first, just a few things. So what is energy, the relationship between energy and power? Because they're a little bit different. Most of us, when say we consume energy, we refer to both of these. But oil is energy. So energy is stored fuel for use at any time. So those are the things that we put in our cars and our planes and our trucks, and we can drive around with those things. That is energy. Power is electricity. That's for immediate use. And the reason we differentiate between those two is because energy, fuel, we can store. We have a very difficult time storing power. Power can be generated from things like solar and wind and geothermal and nuclear power, but right now we have a very difficult time storing it. Battery technology is getting better, but it's still a fair ways off. And so we really need to think about these things as two separate things. And if we look at, how we consume energy, this happens to be in this country, but it's about the same worldwide. The pie sort of breaks down like this. So 36% of this comes from crude oil, from petroleum, from fossil fuels. Okay? And that number is growing all the time. And the main reason that number is growing, as I'll show you in just a minute, is because the rest of the world is trying to catch up to us and our lifestyle, which means everybody else wants a car and wants to be able to drive it around like we do. 23% comes from coal, 27% comes from natural gas. Obviously, burning any one of those three releases the greenhouse gas CO2. Uranium right now makes up about 8% of our use, and hydroelectric about 5 or 6. Renewables, obviously a very small number, but as I'll show you, that number is going to have to grow. Okay, so energy is the world's largest market. Right now in this country, it's a little over $1 trillion. Worldwide, it's about $5 trillion. Just to put that in perspective, all health care in this country is about $150 billion. So it's almost 10 times larger than that, our energy consumption. Interestingly enough, we did not really start using petroleum in the world or in this country until 1900. We started drilling wells in the 1850s and 1860s, but up until 1901, most of that energy was used simply for kerosene lamps. But then, obviously, in 1900, we invented something here called the automobile, and that's how our use has grown. So today, it's about $5.8 trillion. That's worldwide use of energy, on its way to 2020 of about $10.4 trillion. Now, if you look at population growth, obviously the population has increased over that time, but the population is not going to double in the next 10 years. So why does that number go up so much? That number's going up so much because right now, I'm sure as many of you know, Michael, do we have a pointer? I did not bring one. I'm sure as many of you know, in the United States, we consume a little over 20% of the world's total energy. But this is a very interesting graph, and I think it shows something very important. And what this is simply a plot of gross domestic product versus energy consumption. Right? So by and large, what you see is that most people fall along a line that is essentially 45 degrees, meaning that as you consume, as you're a more productive, this one? Yeah. Okay, so here's gross domestic product. So this is how much money you make per capita. This is how much energy you consume. Here we are up here. So we're one of the, obviously, the richest countries in the world, and we're also one of the biggest energy consumers. Now, if you happen to live in Canada, you don't quite make as much money as us, and you burn a little more energy than us, and that's because you're burning some of that energy to stay warm. If you're down here in Saudi Arabia, you burn almost as much energy as us, even though you make a fraction of the gross domestic product we do, because you have so much of it there, you don't care that much about it. And that's also the same is also true for Russia. Right? And actually the same is true for the Canadians. By and large, these guys have the petroleum, so they burn it. Obviously, if you're Japanese, you're a little more efficient than us. You live a little closer together. But what's important about this is not just that without oil, our gross domestic product would drop back and we'd be no better than the French. That's certainly a concern to me. But that's not the really big point. The big point of these two dots right here, that's India and that's China. So as many of you know, there are 360 million of us. There are 2.6 billion of them. And all of these guys want to have the same lifestyle as us. They all want to have the same gross domestic product as us. And the only way they're going to get from here to here is by going energy consumption from here to here. And I'm certain, as many of you will also know, those are the two countries, India and China, that are the fastest growing energy consumers or energy users. And in fact, the Chinese are now out all over the world buying up energy resources as fast as they can. So the oil rights in Iraq were purchased by the Chinese oil company last year. The tar sands in Canada were purchased by them this year. And they are rapidly outbuying every source of energy on the planet because they want to go from there to there. So since we use 20% of the world's supply, and since 10 times as many people as us want to catch up with us, that says something has to give. So that got me to actually look around and saying, well, how much hydrocarbon, how much petroleum is really left? So when will the end of the hydrocarbon era come? So this is the total world energy reserves, and these are reported in what's called terawatt years. So this is simply a way to convert whether it's petroleum or electricity or nuclear or natural gas. So this is just converted into energy consumption. So right now, worldwide, we use about 15 terawatt years of energy per year. But we're going to continue to grow that at about 2.3%, mainly because the rest of the world is going to catch up with us. But if we converted all of coal, so this is every bit of coal that's known that's out there right now, we would get about 1,013 terawatt years of energy out of that. If we converted all the oil, about 582, natural gas, 539. This is the one that kind of amazed me, nuclear. Only between 60 and 300 terawatt years of uranium are actually available out there. I always assumed that, nuclear power plants would go forever. They don't with uranium. They can with something else called a breeder reactor. By its name, you can probably get the idea of what it does. It actually makes more nuclear as it goes. Some issues with that. But if we add all of this up, we come up with a number that's something around 2,000 to 25,000 terawatt years total reserve of energy left in the world. And if we simply divide that number by 15 terawatt years growing at 2 to 3%, we find out that we will run out of all energy reserves before the end of this century. Everything, right? That's everything that we know that's out there, everything we've ever found. That, to me, was a really alarming statistic. And in fact, if the world were to jump up to the U.S. consumption rate right now, we would be completely out of all hydrocarbons by 2048, right, in less than 40 years from now. That number I found a little bit concerning to me. But here's a really nice graph that I stole off the internet. This is simply oil production and use and the time frame between the birth of Christ and the year 25,000. So we used virtually nothing until 1901. We hit our peak in this country in the mid-70s. We hit peak oil worldwide. We hit it in 2005. And then it's going to come back down and we'll be gone before the end of the century. And in fact, there's no reason, this is arbitrary that I started it here. This number could actually go back 200 million years. Because what petroleum is simply, petroleum is ancient algae, and coal are ancient fossilized plants, and they have been piling up for the last 200 to 300 million years. So in fact, we have used 300 million years of accumulated hydrocarbon in a span of about 200 years. And that to me is really quite alarming. Now some people will tell me, and I've had actually people in the audience say, oh, that's not true. We have not reached peak oil, right? We're going to continue to find this. In fact, as the climate changes and the globe warms and the polar ice cap melts, new areas to go searching for. And in fact, ironically, there's truth to that. And the Vice President of British Petroleum, bless his heart, before we had our little mess in the Gulf, actually said, climate change and global warming isn't all bad. We'll be able to explore for petroleum in new areas that we couldn't before. But what this is simply a graph of past discoveries and then projected future discoveries down here of oil fields. And this, by the way, is from ExxonMobil, so I think they got this one right. And then the black line is production. So what we've actually improved dramatically over the last 20 years is our ability to recover diminishing amounts of oil that are still left in the ground. So we've gotten much better about that, and that's kept us up. Otherwise, as I said, we actually hit in the United States peak oil in '75, and this would have gone back down. But we've gotten very much more sophisticated about how we pull it out. So we sort of pushed that off. But starting here in 2005, this started to drop down, and it'll just continue to decrease going out here. And when that number really runs out, is completely dependent upon how we decide to conserve this resource. But, you know, so people, I mean, you can still argue about this. You can say, look, we're going to find better ways. You know, in the Gulf of Mexico now, or off Brazil, we're at 38,000 feet. We've drilled down to 38,000 feet deep to get oil. We'll just keep going deeper. We're going to find more of it, right? But I think another really good way to look at this, and this comes from, you know, sort of my having started a couple of biotech companies, that I realized that if you really want to know the truth about what's going on and, you know, sort of get rid of all the spin, follow the money, right? See where the investors are putting their money in, see where people are spending their money, because people are generally not too foolish with their money. And so I think this is a great way to tell you how much petroleum we really have left. And this is, what's our energy return on investment? And that means how much energy or how much money does it take to get that oil out of the ground? So in Saudi Arabia and in West Texas, the return on that is about 100 to 1. So for every buck you put in, you're going to get $100 back out. Or for every kilojoule of energy you put in, you'll get 100 kilojoules back out. The energy return of investment in the Alberta tar sands is less than 5 to 1. And the fact that we are doing this to the environment and that we are exploiting this resource to get petroleum out tells you how little we really have left. The other thing that told me how little we really had left is when I got a call from one of the ministers, the oil ministers in Saudi Arabia a few months back, and he asked me, have you ever considered using algae to convert low-quality heavy oils into higher-quality light oils? And I said, no, I've never thought about it. He said, well, do you think you could do it? And I said, well, let me ask the guys in my lab. We'll do a little searching and see what we can find. So we did a little searching, and it turns out there are lots of algae that will eat oil. So even in the Gulf of Mexico right now, they're getting nice oil, they're getting nice algae blooms, because these things have evolved over time to actually eat the hydrocarbons. They produced them years ago. They know what they are. They recognize them, so they eat them. Well, if you can get a bug to eat it, then maybe you can get a bug to convert it. So we looked at it a little bit, and I called him back, and I said, well, you know, we think we could do it, but it would definitely be a research project. But I have to ask you, you guys are the Saudis. You know, when last I looked, your oil reserves haven't dropped one bit since they were first reported in the mid-'70s. You say you still have the same amount left. And he laughed and said, oh, I wish that were true. How soon can you get out here and we can start talking about this? So when the Saudis are telling us that they're starting to run out of oil, then I know it's serious. Uh-huh. Yeah.
Decided how much money they can make. The Saudis have been very late on releasing what the reserves are.
Right.
Just like the city of San Diego was supposed to talk about the budget. They were late.
Yeah.
So it's like, there's a reason maybe to be late. Maybe you're inefficient, or maybe it's not to your advantage to let people know what you don't have.
Oh, yes, no, I'm certain of that. Right. I'm certain that we're not being told the truth by them. But what I think the truth is that whether we run out of oil in 10 years or 40 years or 50 years, we're burning through this stuff. And the Saudis have been burning through it faster than anybody. Yeah, yeah. Oh, yes, as I said, just follow the money. I'm certain that's what's chasing it. Yeah. Yeah. Till the end. Yes, because otherwise we're going to run over. Okay, so how are we going to replace this? We're going to run out of it at some point. How are we going to replace it? So the first thing you have to understand, and this always makes me sound like I'm really sophisticated when I use the first law of thermodynamics, but it's actually a very simple law. And what it says is energy can neither be created nor destroyed. It can only be transformed from one state to another. So what that really means is we can't actually create energy, right? We can find it in the ground. We can get it from the wind. We can get it from the sun. But all these are forms of energy, and then we convert them to another form. So how can we actually use that information? Well, as I said, right now the world consumes about 15 terawatts of energy every year. 85% of that is derived from fossil fuel. But the really good news, and this is probably the only good news I'll give you all night, the really good news is that the sun provides 86,000 terawatts of energy every year onto our planet. So 6,000 times more energy lands on us than we actually use to drive our cars and heat our houses and light them. So that's pretty good. I mean, 6,000 times, we don't have to be very efficient. You know, 0.1%, and we're home free. All right, so how are we going to convert that? So what biofuels are biofuels are the biological conversion of sunlight energy into chemical energy. And that process is called photosynthesis. So what it does is it takes sunlight energy, water, and CO2, pulls the CO2 out of the air. You also need some nitrogen, some phosphate, et cetera, to help build the machinery. And then that converts it into chemical energy. So you're taking sunlight energy, CO2, and you're converting it into chemical energy. And that chemical energy can be in many different forms. So it can be in hydrocarbons. It can be things we can drive our cars around. It can be in carbohydrates. Those are sugars, things that drive us around. Or it can be in proteins. You can make any one of those three from it. And all of these are simply different forms of energy. So in fact, one of the things that's been a little bit lost on the debate of as we run out of hydrocarbon, what are the consequences are going to be, is what this tells you is that the conversion of food and fuel is a simple conversion, and that we can actually think of those two things as the same thing, right? So you often hear this debate, well, are we going to have food or are we going to have fuel? Well, in fact, they're two different forms of the same thing, and we can convert between those. And that's exactly what corn ethanol is. So corn ethanol is simply I take sunlight, and by photosynthesis I make corn, or this could be sugar cane, or this could be whatever carbohydrate I want. And then I can ferment that carbohydrate into ethanol, and I can burn that in my car. So I can take food and I can convert it directly into fuel. Now there's a big debate on whether we should do this, you know, whether if we're taking corn to drive our cars around, who's losing that corn, right? And that is a debate that we will, I hope, engage in later tonight. Now, you can also do something that plants will also make cellulose. They'll make wood, they'll make fiber, and in that are carbohydrates, and we can actually take those, break those down into sugars and ferment those into ethanol. And that's called cellulosic ethanol, right? And many people imagine, oh, we're going to take some of our waste cellulose that's out there, some of our trash, and we're going to convert that to fuel. And you can also take that and actually burn it for electricity. And that's a perfectly viable, renewable energy source, right? Now, it turns out that we can also take algae, and by photosynthesis, algae, instead of putting its reserves into carbohydrates or proteins, it chooses to put those into natural oils. That's its storage form of energy, and that's simply a biological function of the organism. It decided that it wanted to do that, to store energy. And we can take these natural oils, and we can actually readily convert those into fuels. So why do we think of algae as a sustainable energy source, as a bioenergy source? There's really several things. So first of all, scalability, and we'll talk a little bit about this. We burn in this country 300 billion gallons of petroleum every year. 20 million barrels a day, 365 days a year. So if we really want to make a dent in our energy landscape, we better get something that can go to pretty big scale, okay? Obviously, we need productivity. We want to be as efficient as we can about that. We'll describe that a little bit. Here's the important thing. We want sustainability. And that means that we can do this every year for a very long time to come, that we're not using up some other limited resource in order to produce this energy. And finally, it's really nice if we can have what's called a fungible fuel or a drop-in fuel. So ethanol, as some of you may know, even though we can burn it in our cars, it's kind of a crummy fuel. It only has about 70% of the energy density of petroleum or gasoline, so it's too light to fly an airplane on, for example. And then it also has some issues of bringing water along with it and being corrosive. So even though ethanol from sugarcane is successful down in Brazil, you have to change the entire infrastructure in order to make that go. So the nice thing about algae is we actually make fungible fuels. So we make what's called drop-in fuels. But as I said, the most important thing, I think, is that we have to be sustainable. So I'm sure many of you have seen the debate on corn ethanol. And the debate on corn ethanol says, well, okay, we can make ethanol from corn. And in fact, in this country, we make 8 billion gallons a year of corn ethanol. Next year, that number is going to go up to 12 billion. And I don't know if any of you have noticed, but the new farm bill that's coming along says we should push that out to 20 billion gallons per year of corn ethanol. But if you do something called the life cycle analysis, so that means you measure all of the energy in, right? So how much energy am I going to put into that corn that I can get a gallon of ethanol out of it? So that is planting the seed, driving the tractors to harvest it, fermenting that sugar into ethanol, distilling the ethanol off. If I add up all of the energy in, it turns out that it takes as much energy into corn as I get out of it when I turn it to ethanol. So it actually takes a gallon of petroleum, convert it to fertilizer, convert it to driving the tractor to make a little more than a gallon of ethanol. But the energy density is less, so it comes out about a wash. So then you'd think to yourself, well, that's not sustainable. Why would we do that? Why not just take the petroleum? Well, the reasons for that is because in this country we have a very strong farm lobby, and they would like to see farmers fully employed and working. So they wrote legislation that says we should have corn ethanol mandated. And I think many of us scientists, but many even the economists looked at this and didn't realize that it wasn't going to be that good. You know, we assume that, well, you're still using photosynthesis to turn it into this. There has to be energy input in. So corn turned out not to be the best choice for that. Sugarcane in Brazil works a little better because they don't have to put as much fertilizer on it, because they do a lot of their harvesting by hand, and because you can actually burn the excess sugarcane called bagasse. You can burn the cellulose in it and use that to drive the ethanol off the water, and that's a big energy use of this one. But when we look at cellulosic ethanol, or when we look at algae and do a life cycle analysis, that turns out to be a much better number. So when you measure these things, you actually measure it in grams of CO2 released per millijoule of energy. So when we burn that in our car, right here, when in combustion of that, so if we just take a gallon of petroleum and burn it in our car, we're going to release about 74 grams of CO2 for every millijoule of energy that we get out of that. In addition, it takes about 21 grams of CO2 to pull that oil out of the ground and refine it into a fuel. So the net gain of that, or the net output of that, is about 95 grams of CO2 for every millijoule of energy out. Now, if we look at algae, fuels made from that, and the same would be true for cellulosic fuels. Okay, we're going to get the same release of about 72 grams of CO2 when we burn that in our car. That number is actually a tiny bit smaller than that number, because actually the fuels we get out of algae are a little bit superior to the fuels that we get out of petroleum. But the number's about the same, so that's 72 grams of CO2 that are released. We also have a production and refining cost, which is about 30 grams of CO2 per millijoule. So you add those two up together, you get about 102. But what you get is that you get a net negative of 71 grams of CO2 from photosynthesis. So what that means is that the algae are pulling CO2 out of the air in order to make the fuels that they're going to release. So the net outcome of that is that it takes us about 31 grams of CO2 for every millijoule of energy we get out. Now, what we hope is that we can make improvements on the production and the refining process here, squeeze that number down, because every gram we squeeze out of that directly comes out of this. So can we ever get these to what people will say carbon neutral or carbon zero fuels? It's unlikely. But we think we can get this number down to maybe 10% of what we get out of petroleum. Yeah?
I think your first graph was specious in the sense that the genesis of petroleum was just millions of years ago. That CO2 was pulled out of the air too.
Of course, but it's been sequestered underground, so it's not released as a greenhouse gas. As long as we leave it underground, it is not contributing any CO2 to the atmosphere. I mean, some of it does bubble off, and occasionally we do get natural spills in it, but most of the stuff gets released when we go down, drill it, and pull it out. So we'd say that's desequestered CO2. Okay? Yes, but you're right. That all came from photosynthesis. You know, that's back to my first law of thermodynamics, right? It was simply a solar conversion to that stuff thousands of years ago, sequestered CO2, released oxygen in the atmosphere. That's why all of us are alive today. That allowed mammals to exist, okay? When we go back the other way, and it's all CO2 and the oxygen's converted in that, then we cease to exist. Okay, so thank God there was photosynthesis. Thank God it showed up a couple billion years ago. It allowed all of us to be here. Okay, so what is the process? The process is we grow algae. Obviously, we're not going to grow it in little bags like this. We're going to grow it in something much larger. But this is what a company that I started called Sapphire Energy actually did. This is one of their small pilot facilities. You harvest that algae. You extract the oil out of it. You concentrate that, and that goes directly into an oil refinery. And you can crack that, into gasoline, jet, or diesel. So in January of 2009, we took oil from algae, we cracked that into jet fuel, and we flew a Continental Boeing airline on that for 90 minutes. And it performed up to spec, the same as the Petroleum, which was powering one of the other jets. In August of last year, we took a car called the Algaeus. It's a Prius. We loaded it up with algae-made gasoline and drove it from San Francisco to Washington, D.C., switched the engine out and put a diesel hybrid engine in it, and then drove it back from DC to Los Angeles with diesel also derived from algae. So we can make these things. That's not the issue. We can take algae, we can get oil out of it, we can crack that into to gasoline, to jet, or into diesel fuel right now. The problem, as many of you can probably guess, is how much does that cost and what scale can we really go to? So the other good news is we sort of know what the production chain of this looks like. We know where the improvements are we have to make, right? We have to start, we have to get the right strain. This is just like agriculture. You know, if you went out and just took weeds and threw them out in the field, it would be unlikely that you would ever get anything that looks like corn or oats or watermelons. We had to select those over thousands of years. But we've done that, and so we need to do the same thing with algae. And then, of course, obviously, we need to work on our inputs, water, CO2, et cetera, get our pond designs up, harvesting. So we know what all of these looks like. And here are really the big 5 places where we know that there's an opportunity for us to make the economic advances we need to make to get these fuels, which we can already make, down to economically competitive prices. So that sort of looks something like this. So right now we're what I'd say we're in the bioprospecting era, meaning we're out looking for the best strains of algae. We're looking for ones that grow very fast, that are easy to grow. You know, some strains of algae are a little fussy, just like plants. You know, I managed to kill some of my plants, but some of them are a little hardy and stay on better. So we need to find those guys, and we're doing that right now. And some of these produce naturally high levels of oil. And so we've already got ones that grow fast enough and produce about 30% lipid. So the economic viability from bioprospecting has already been achieved. Now we've entered into the era right now of doing engineering, breeding, selection, et cetera, first of all, to get these things resistant to pathogens. So like any agriculture, one of our biggest problems in growing algae outside is that a lot of things want to come in and eat it. We get fungus that come in and eat it. We get these fantastic little monsters called rotifers and daphnia that land in the ponds, and they just look like little things out of Star Wars, and they go by and they graze on your algae. So these are insects that are coming along to eat it, and we need to find ways to protect our algae from that, exactly the same way we have in agriculture, right? Exactly the same way we have to get protection from grasshoppers and mites and et cetera, and fungus and that. We have to do the same thing. Then after that, what we've got to do is we've got to do a little bit of economic viability, which makes co-products. So the expression in agriculture is the only way you can be successful in agriculture if you're working on pigs is you sell everything but the oink, right? So you have to monetize every part of that. So we already know that we can get 30 to 40% lipid out of these guys. We have to find out what we're going to do with the other 50 to 60%. And as I said, most of that is protein, so we think there's some opportunity to turn this into animal feed. So why am I optimistic that we can do that? I'm pretty optimistic that we can do this in a pretty short period of time. So that's called domestication, and this is what we do very well in this country, right? So in corn, it took us a little longer than we better spend on our biofuel algae. It took us about 7,000 years to go from this scrawny little guy here, which is called teosinte, up to this thing right here, which is called B39 dent corn. This little thing right here feeds the world, right? This thing right here wouldn't feed too many people in the world. So we need to do the exact same thing in algae, and we've done this on every single crop we've gone out there. We've done this on beef, we've done this on chicken, you name it, right? Domestication of those guys. The good news about algae is because it's a microorganism, we can do this relatively quick. But this is one of actually my favorite graphs. This comes out of, so this is corn production in the United States, and this number could have gone back forever. Sort of forever, we were at about 20 bushels per acre. And then in 1930, DuPont started to introduce industrial practices and breeding, genetic crosses between species. And when they started to do that, the productivity started to go up. And then in the 70s, we started to introduce molecular science into this. And because of that, over the last 90 years, we have increased corn yield 7-fold, 700%. And thank God we have, because there wouldn't be 6.6 billion of us on this planet if we hadn't done this with corn and all the rest of our crops we've done this with as well. Rice, soybeans, you name it. So I think there's an opportunity to do that in algae. The other thing that's really wonderful about these guys is they have populated every ecological niche in the world. And in fact, if you look at the diversity of algae, so here's cyanobacteria. These are photosynthetic bacteria, but they're related to algae. Here's brown algae, green algae, red algae. And this is just sort of a phylogenetic tree. And what this says is the farther apart the two little lines on this, the more different you are. So cyanobacteria are very different from red algae. Brown algae is very different from red algae. And just to put it into perspective, so C. elegans, those are nematodes. Homo sapiens, that's people. So I like to think I'm pretty different from a worm, but that's how close we are together as being a couple animals on this compared to red algae and brown algae. So what that really means for us, what the opportunity that presents, is that we have a fantastic reservoir of traits, of photosynthetic traits out there that have evolved over the last several billion years that we can now exploit. And one of the things that we're starting to think about now and that we're starting to talk to ag companies about now is, you know, going forward as we're running out of petroleum, we're going to use less nitrogen, less phosphate fertilizer. We all know that we're running into water shortages. Well, algae have evolved. There are algae that can survive in 4 molar sodium chloride. So that is salt that is so concentrated there are crystalline salt in that solution, and yet there are algae that can survive in that. So clearly they have evolved, they have adapted, and they have developed a set of genes that allow them to do that. And if we can understand that from algae, I think we'll have the opportunity to maybe introduce some of these genes into higher plants. In other words, we might be able to get corn plants that can tolerate being watered by salt water. You know, we imagine at some point we may actually be able to go to saltwater agriculture, something we've never even considered before, right? Now, this will take a little bit of time and a little bit of engineering, but I think the opportunities are there. Okay, so can we really replace petroleum with algae oil, right? Can we really get to that 300 billion gallons per year that we use? So this is simply a picture of the Nylon algae farm out in Imperial Valley. This is one that the San Diego Center for Algae Biotechnology uses as one of our test facilities. Each one of these ponds is about 400 feet long by about 25 feet wide, and they hold about 400,000 liters of algae. And they're under high production, okay? But if we just look at the numbers, so here are just a few numbers to consider, and what do we really have to get to? So as I said earlier, we burn about 20 million barrels of oil per day in this country. We import, as many of you I'm sure know, about 15 million of those. Domestically, we produce about 5 million. That 5 million number is dropping quick. That equates to 300 billion gallons per year of petroleum. So algae can produce 50 tons of biomass or 5,000 gallons of oil per acre per year. So the simple math of multiplying 5,000 gallons times 60 million acres, that would give us our 300 billion gallons of liquid petroleum that we use. So you say, oh, only 60 million acres. That seems like a really large number. Like when I first looked at that, I thought, oh, that's hopeless. 60 million acres, that must be half the United States, right? But actually, it turns out that 60 million acres isn't such a big number. Well, this simply shows, this is simply to show efficiencies on why we would use algae over these other guys. It's much more photosynthetically efficient. But that's not the important point. The important point is, what is 60 million acres? Well, so this is, how many acres of crops do we have in the United States right now? Well, corn, presently we're about 90 million acres under production. 30 million of those are used for corn ethanol. So half of the number that we need in algae to replace all of our petroleum is used for corn ethanol to get us 8 billion gallons, a few percent of our requirements. Soybean, we're at about 75 million acres, and wheat, we're down here at about 55 million acres. So these are numbers we understand. These are numbers that American agriculture is used to dealing with. 60 million acres is not that big of a challenge. Getting to 60 million acres, that's a challenge. Okay? So where does all that corn go? I mean, we have 90 million acres of corn. Where does it go? As I said, 25% of that crop last year, this was actually 2007, 25%. Now it's up to a little over 30%. That goes to corn ethanol. 45% goes to animal feed. 19% we export to other countries. How much actually goes to human food? 1.5% of the corn we produce actually ends up in corn checks or something we eat. Actually, a little more of it ends up because one of these down here, alcoholic beverages, okay, so I have to count that, 1.1% we actually consume those. And high fructose corn sweetener, that guy right there, that gets put into almost everything. In fact, the rumors I have, and I don't know if this is true or not, that if you go to McDonald's, it's 70% of what you eat. I don't know if that's true or not, but that's what I've heard. So we do use corn for some other foods. But the vast majority of this goes into feeding animals or to turn into corn ethanol. So we have the acreage available, right? We could do this tomorrow. One last slide, we'll go to questions, all right? So I'm going to leave it at that. We're going to open it to discussion. I know I talked too long. But I just want to tell you, you can follow us at the San Diego Center for Algae Biotechnology. That's our webpage, and you can sort of log on if you want and follow the latest and greatest that we think we're up to. And then we will open it for discussion. Thank you all.